Hello everyone, I am M.Sathyavathy, Assistant Professor from Science and Humanities Department. I am going to explain about the concept random processes. Before we moving to the topic, let us see the motivation behind the random process. The concept of probability and random process play a vital role in wireless communication system. Let us see an example. It's a base station and it is a mobile station. Let us consider trees, buildings. Yes. Base station, which is transforming the signals to the mobile station. That is, the signal is received by the mobile station. There are number of reflectors are there in the wireless environment. These reflectors are random, and these reflectors are large objects like trees, buildings, which are also known as scatters. Hence, there are number of signals, and these signals are randomly received by the mobile station. There is a large amount of in-depth error. Hence, the signals received by the power, amplitude and the mobile station are random in nature. Hence, the concept of probability and random process play a vital role in understanding wireless communication system. Right. Next, we are going to see the prerequisite which is going to use for random processes. Prerequisite for this course. The prerequisite for this course is the basic course of mathematics like sets and calculus, both differential and integral calculus. So, if those who knows the concept of sets and calculus, they can easily understand the concepts of random processes. Right. Now, I am going to explain some basic elements of probability model. Basic element of probability model. Under the basic element of probability model, the first and the foremost model is the experiment. Experiment. Usually, we will have two type of experiment. One is the experiment which is we usually do in the laboratory like physics or chemistry. So, in this type of experiment, the outcome is already known. A random experiment is an experiment or a process of which the outcome cannot be predicted with certainty. So, outcome cannot be predicted with certainty. Right. What is outcome? Outcome is nothing but the result of the experiment. Result of the experiment. And one more thing, outcome of the experiment is always well defined. Right. The second component under the probability model is sample space, which is denoted by ohm. Right. All possible sequence of the experiment is called sample space. So, all possible outcomes is called sample space. Right. Now, I am going to explain some examples for this experiment and sample space. So, let us consider experiment number 1. Yes. So, for this, I just take a coin. Oops, it falls down. This is an experiment. Let us look at the outcome. So, the outcome is I just get head. This is my experiment. So, the experiment number 1 is toss a coin and look at the outcome. Right. So, this is my experiment number 1. The sample space corresponding to this experiment number 1 is, according to the definition of the sample space, all possible outcomes is called the experiment. Right. So, in my experiment number 1, toss a coin and look at the outcome. So, what are all the possible outcomes for tossing a coin? Head or tail. So, all possible outcomes are head and tail. Right. Now, let us consider another experiment number 2. The same, toss a coin until head appears. Right. So, for this experiment, the sample space 2 is, right, I just toss a coin until head appears. So, all possible sequence lies in my hand. Potentially, the outcomes goes on forever. So, what are the outcomes over here? Head, TH, TTH, etc. Right. Could you note the difference between experiment number 1 and experiment number 2? In experiment number 1, it is finite. Right. The experiment number 2 is countable. Whether it is finite, it is infinite. So, it is countably infinite. Right. Now, let us look some interesting experiment, not rather than the usual coin tossing experiment. Right. So, experiment number 3, throw a dot into a circular region of radius r and check how far x from the center. Right. So, throw a dot into a circular region of radius r and check how far x from the center. So, for this, I just take a circular region of radius r. I ask someone to throw a dot inside the circular region. To throw a dot inside the circular region. The force that is in a particular point or an arbitrary point lies inside the region, that is lies inside the circular region. Right. And my outcome is how far this x away from the center. So, this is my outcome. So, what is the corresponding sample space for this experiment? So, sample space 3 is x such that x should lies between 0 to r. What kind of x I will have? X belongs to real number. Right. So, this is my experiment number 3. Right. Now, the another probability model, the third thing under the probability model is event. So, first one is experiment, second one is sample space. We just look at some examples for this experiment and sample space. Now, I am going to explain the third component under the probability model. It is the event. So, the third one is event. Event means it is the subset of the sample space. It is the subset of the sample space. Sample space. The event is denoted by any alphabet. Let I consider as A. It is the subset of the sample space. Let me see one example under the event. So, for this, I just the same using the experiment as a toss a coin, getting head before fourth toss. So, the event is the same coin tossing experiment, but getting head before fourth toss. This is my event. right. So what are all the terms over here? So A is equal to H, TH, TTH. So this is my event. This is my event. So let us consider this is the event for this example. Sir, கொஞ்சம் easy on பண்ணுங்க sir. Right. So this is the event, but according to the definition of the event, it is the subset of the sample space. So how could we check whether it is a subset of the sample space? So for that, let us consider the event toss a coin until head appears. So what is the corresponding sample space for tossing a coin until head appears? It is head, TH, TTH, etc. Right. So let us check. Event is the subset of the sample space H, TH and TTH. Right. Could anyone say what is the outcome for tossing a coin for 3 times? What is the outcome for tossing a coin 3 times? Toss a coin 3 times and check out the outcome. Right. So for this, I just consider the first time head, tail. Second time, this is the second time, first time, second time, and again third time. Right. So the general notation for getting the outcome is 2 power n. N represents number of times, but here I am tossing 3 times. So 2 power 3 represents 8 possible outcomes. Let us check. So H, H, H. Then HHT, then HTH, then HTT, similarly THH, THT, TTH and TTT. So up to we will have 8 possible outcomes. Right. So still now I have explained some basic probability model. Now I am going to say how could we assign the probability for the event or the set. So assigning probability, assigning probability. Right. So for this, let I take an example as throwing a die. So example, throw a die. Right. So I just throw a die. What are the sample space for throwing a single die? 1, 2, 3, 5 and 6. So this is the sample space for corresponding throw a die. Now I consider event from the experiment. Now my event is I just consider getting even numbers. Getting even numbers as a event. So if I take getting the even numbers means 2, 4, 6. So this is my corresponding event under the experiment. Right. So let us assign the probability for this. This is nothing but favorable case divided by total number of items. So what are my favorable case under the probability of an event? 2, 4, 6. So 3 terms. Number of favorable case 3 divided by total number of items in the sample space is 6. So you get 1 by 2. So this is nothing but 0.5. It is interesting to know the probability of an event should always lies between 0 and 1. Let I explain this about later. Before that, let I going to explain some important axioms or laws under the probability model. Axioms. The first axiom is the non-negativity. That is, probability of an event always greater than or equal to 0. That is called non-negativity. The second axiom is if A and B are two disjoint sets, let A and B the disjoint set, according to the additivity we will have probability of A union B is equal to probability of A plus probability of B. This is a second axiom. The third one is normalization. This means probability of a sample space is, could anyone guess what is the probability of a sample space? Let us check. So usually the sample space means all possible outcomes. So the probability value means total number of favorable case divided by total number of items. So all possible outcome is called sample space. On the whole, its value is 1. Right. So these are all the important axioms under the probability model. Right. Now I am going to explain an important property under the probability model. That is a property under the probability model. Right. So what is the property means? The probability of an empty set is impossible. So it is 0. Let us check how it is possible. Right. So for this I just consider a two disjoint set. Right. So sample space union empty set is sample space. Now I am going to apply axiom number 2 over here. That is probability of a sample space. I am going to apply probability over both, and by applying axiom number 2, axiom 2. So we get like this. According to our axiom number 3, probability of a sample space is 1. So I just apply axiom number 3. So from this we get probability of an empty set is 0. Right. So these are all some important concepts. Already I told the probability value should always lies between 0 and 1. Let us check how this is possible and how could we say that probability values lies between 0 and 1. For that, let you take any event. Let A be the any event. Right. According to the definition of the event, it is the subset of the sample space. Right. Then we take a complement for the event, and by disjoint we take A intersection A complement is, could you say what is A intersection A complement? It is empty set. Right. Again A union A complement is, it is a sample space. Right. Now I am going to apply axiom number 2 over here. Right. This is applying axiom number 2. Now I am going to apply, before that we can bring this term for our convenience, we just bring this term to right hand side. Right. Now I am going to apply axiom number 3 over here. Right. So from this I just bring this term to right hand side. It becomes probability of a sample space minus probability of A. Right. Now I am going to apply axiom number 3 over here. So our axiom number 3 is probability of a sample space is 1. So this becomes probability of A complement is equal to 1 minus probability of A. Right. According to our axiom number 1, probability of any event should be greater than or equal to 0. Our axiom number 1 is non-negativity. By comparing that, I just take probability of an event, that is A complement, as probability of A complement is non-negativity. Now from this I will have 1 minus probability of A is also greater than or equal to 0. Therefore probability of A is less than or equal to 1. From the axiom number 1, probability of A is non-negativity, that is probability of A is greater than or equal to 0, and from here we get probability of A is less than or equal to 1. So therefore on the whole we get probability value should always lies between 0 and 1. So that's why we are getting the answer in the probability between 0 and 1. Right. Now I am going to explain about random processes. Before we moving to random processes, we want to know what is random variable. Usually the outcome of the experiment is not a number. For example, the sample space could consist of the outcome, success and failure. So this is the sample space would consist of the outcome, success and failure. It is useful to assign a number to the sample space, that is the outcome of the sample space. Let I assign a number as success is equal to 1 and failure is equal to 0. Right. So that's why assigning a number to the outcome sample space is called a random variable. It is defined as x such that S tends to Sx. X is the random variable and S is the sample space of the experimental outcome. Sample space of the experimental outcome. And Sx is the sample space of the outcome of the random variable x. X such that S tends to Sx. Right. So this is a random variable. Now we are going to move random processes. Now we are going to move to random processes. Right. Random processes means the random variable which is a function of time t is called random processes. So random process means random variable which is a function of time t is called random processes. That is random variable which is indexed by time t. Random variable which is indexed by time t is called random processes. Right. Let us consider an example for this. Consider a random experiment of rolling 3 dices. Let us consider a random experiment of rolling 3 dices. Right. First I consider a first die. A die can turn up with any one of the time instant and it gets the possible outcomes. First I throw a die. At any time the die can turn up with any one of the random numbers. So what is our die turn up? Any one of the random numbers, that is 1 to 6. Similarly, the other 2 dice also can turn up with any one of the random numbers. At any time instant, we get the set of 3 random values. 3 random values which constitutes a random variable. Repeating the same experiment for different time instant t, we get the set of different random variables. This constitutes a random processes. This is an example for random processes. Right. Now I am going to explain the classification under random processes. Classification. Right. This random process is being classified by its characteristic either by random variable and by time t. This is random process is being classified by the characteristics random variable x and time t. right. It's been categorized into 4 categories. That is discrete, random process, continuous random process. Similarly, discrete random sequence, continuous random sequence. How could we classify these 4 categories? Through X and T only. Random process, which is called discrete random process, if X is discrete and T is continuous. What is continuous random process? If both X and T are continuous. What is discrete random sequence? Both X and T are discrete. What is continuous random sequence? If X is continuous and T is discrete, is called continuous random sequence. So these are all the classification under the random process. Now we are going to see, already I said random process means a random variable which is a function of time t. Corresponding to every time instant t, we will have probability density function which is also therefore indexed by time t. So already I said random process is a function of time t. Corresponding to every time instant t, there will be a PDF, probability density function, which is also therefore indexed by time t. Indexed by time t. This is denoted as probability density function. It is also therefore it is denoted as capital Fx of x comma t. This is also indexed by time t. Right. Now we are going to see some statistical measures under the random process. Statistical measures. This means we just consider average value of the random process or a mean of the random process. Sometimes we call this as expected value of the random process. It is denoted as mu suffix capital X of t. Since the random process is indexed by time t and our statistical measures also should be indexed by time t. So mu x of t is equal to, that means expected value, expectation of x of t is equal to integral minus infinity to infinity x into fx of x comma t dx. That is x times the probability density function with respect to x. So this is called probability density function. Right. Now I am going to explain one important property under the random processes. I am going to explain one important property under the random process. It is called a autocorrelation property. Autocorrelation. Autocorrelation. From the name itself we can suggest what is autocorrelation. It is nothing but the self-correlation. It is an important property under the random process. This means that just consider Rxx of time t1 comma t2, which is equal to expectation of x of t1 into x of t2. Right. That means a random variable, we are having two random values x times the time instant t1 t2, which is equal to the expected value of time instant t1 and time instant t2. This is the autocorrelation. Right. Now I am going to see a subclass of random process. Subclass of random process, that is subclass of random process, which is also called a WSS, which means wide sense stationary or weakly sense stationary or sometimes covariant stationary. WSS means wide sense stationary. or weakly sent stationary or covariant stationary. It is known that we are having first thing under WSS is it is known that expectation of x of t should be a constant under the WSS. And second one is we will have an autocorrelation. Autocorrelation factor is also there under the WSS. This means we let I take time t1 as t and t2 as t plus tau. Then expectation of x of t and x of t plus tau, which is equal to Rx of, this is a tau represents the time shift. So expectation of x of t into x of t plus tau is equal to Rx of time shift, time difference. That means t2 minus t1. So t plus tau minus t. Therefore we get Rx of tau. So this is our autocorrelation factor. Now the random process which is not a stationary is called a evolutionary process. Evolutionary. That means the process which is not a stationary is called a evolutionary process, right. So in this module I just explained the basic important concept of probability and the random processes. Under random process we have seen what is random process and the classification of random process, statistical measures and some subclass of random process, that means the WSS. So in the coming next session I am going to explain the subsequence of this sessions. Thank you all.